So hello everyone, my name is Ivo Stratev, and today I will present about consensus in distributed systems as part of VMware's Tech Meetups series. So I'm currently a member of technical staff level 2 as position. If you saw the introduction or the summary of the talk in the Meetup, there is said that I'm working on a high throughput data ingestion service. Well, this is no longer the case. With some of my team members, we just moved to a new project. Now we are working on a database as a service projects. There are currently 2 in VMware. We joined the Moneta one. But yeah, today we'll talk about consensus in distributed systems and more precisely the Raft protocol. So what is consensus in distributed systems and why do we need this? First, let's talk about what we mean by distributed systems. For me personally, a distributed system is any system where there are at least 2 machines that work in some way together to achieve a common task. And when we think about distributed systems, we probably think about databases or things like this. Maybe S3 as a typical distributed storage. But actually, every web app nowadays is actually a distributed system because you have the browser that's running a client-side application, and on the other side, you have the server, and those 2 are working together to achieve a common goal. For example, when you're ordering something from Amazon, you're using their web application, but this application talks to the server. So you have a communication between the 2, and they're achieving a common goal, which is to for you to order something from Amazon. Just an example. Now there are different consensus protocols, so at least the most common are showed here. The first one is Paxos, and there are others. But before we go to this, I would actually like to draw a little things on a whiteboard so we can basically come to why we need this in a natural way. So let me figure out how we started the whiteboard here. Actually, Brian, I guess you're the host, so maybe if you give me the host, I can start.
Yeah, just a second. Should be co-host now.
Maybe I actually stop share and try another way. Does anyone know how to start a whiteboard here? Because I'm not seeing the option.
I'm not seeing it yet either. I'm looking to find it as well.
Oh, I found it. Okay. So when we talk about databases, which are probably some way distributed, we have different options, right? For example, we may have multiple servers, but the data on both servers might be the same, or rather they might manage the same data. So in this scenario, we will have actually a replication between the 2 databases. Probably one of them will be designated as a leader, and the other one will be designated as a follower. And what will going to happen is that the leader database is going to accept all the writes for sure, but it depends on the kind of the database, the consistency model. For example, the forwarder might be able to serve directly read-only queries when we have strong consistency and the communication is synchronous, or the reads might go also to the leader, but the forward one or the replica might be standing just in case if the leader fails, and so it can take over, and in this way we can achieve high availability. So this is one of the scenarios when we talk about distributed systems, and we see, for example, if we have the notion of leader. Why we have usually a notion of leader? Because it's actually a much simpler way to achieve replication and high availability in this way. Just one of the nodes decides the state. We have, of course, multi-leader database and those kind of setups, but usually it's one leader. And we said that we have replication. It might be synchronous, but it also might be asynchronous. What does it mean to have an asynchronous replication? This means that the state changes that happen in the leader database might be asynchronously transferred and copied back to the replica by some form of communication channel. So this is one way for talking about distributed systems, in particular about databases. Another way is to actually have a database that on itself is distributed. So we have, again, multiple servers, but each of those servers might actually handle or control a different part of the data. For example, we may have one of the tables, if we are talking about a relational database, stored on one server and handled by this server, another table by the middle server, and maybe two more tables on the third server. And here, when we have a distributed system, we might have, for example, a transaction that spans across multiple tables. So this transaction will have to be controlled by another server, or maybe by one of the nodes in the system, and might touch on different databases. So we need to coordinate the changes in the two servers, which we usually call nodes or shards, depending on the terminology. But again, we have a distributed system, and usually what actually might happen, we'll probably have the two at the same time. So we might have a distributed database where the data is distributed, but each shard might have multiple replicas. So we can achieve either high availability or to be able to serve read queries much faster. And in this case, we still need to replicate the data. So we need to replicate the data from the leader that holds the, let's say, the writing lease, but those changes will need to be propagated to the replicas. And so we naturally actually come to the idea of state machines that gets replicated, or the so-called replicated state machines. These are actually not the usual state machines that we have seen all in our time as college students, for example, from formal languages. But those are, again, state machines, just not finite. And what's the state of one database? Well, the state is the actual data. For example, if you're talking about key value stores, we might have a value of X for the key with value X, and that points to value 3, or Y that points to, for example, value 5. And this is our state. And as you can see, this state might grow arbitrarily. We might have arbitrary keys with arbitrary values. But this is again a state. But we need to have a way to replicate from from the leader to the replicas, and usually this is achieved by using transaction walk, which is actually a separate thing from right-head walk, which you may some heard of. But usually what's happening in real database implementation is that the right-head walk is actually the same as the transaction walk because it's actually easier to implement. And let me describe what we mean by right-head walk. Okay. So we have one of the nodes that receives, in the case of relational database, it receives transactions. It receives some multiple series of reads and write operations. And when we decide that we are done with one transaction, we commit. And what's transaction? Transaction is just a logical grouping of operations that needs to happen consistently. So we have the leader node that receives transactions, and we need to have a way to first durably store those transactions, because usually relational databases are so-called ACID compliant. So this means that actually what we expect from when we use transactions will usually happen, but this is actually only true when we are using the highest isolation levels, which are either linearizable, linear, or snapshot linear isolation level. But as things progressed, people actually discovered that they can very fastly write and persist the transaction to have their durability aspect of the ACID properties by using something called right-head walk, which usually gets abbreviated as WOW. So what is the WOW? WOW is just usually append-only kind of structure. Well, it usually gets implemented by multiple files, which are usually called segments, but I don't want to go into those kind of details. But the idea of WOW is that we, in order, persist the changes or the actions that each transaction's made in the order that they committed, usually. As I said, this actually, from theory standpoint, is called actually a transaction walk, but usually gets called also right-head walk. While the idea of the right-head walk is to actually take advantage of the append-only benefits of using traditional storage as hard drives, because writing sequentially to hard drives is much faster than doing randomly, because the hard drives needs to spin and we need to change the falls there. But people actually found out that using those transaction walks or right-head walks is actually very simple or good idea to replicate databases. So what they have to do is actually somehow transfer all the records from the transaction walk from the leader to the follower. And this way we can replicate either synchronously when we acknowledge back to the leader that we have persisted in the forward replica some of the entries there, or asynchronously. And some may have heard of the term change data capture, which is actually a way to do this in usually in agnostic way, agnostic for the user of the database, but obviously in implementation detail way for the one who is implementing the CDC. So what are usually those entries in the transaction walk? Well, as we said, they actually contain the writes that happen during the transactions. Why the writes? Well, we actually don't need usually the reads, because we can derive the reads if we know which are the writes and basically know all of them, not just from one transaction, but all the transactions that need to happen so we can reconstruct the reads. I see that some people are maybe trying to ask questions. Are there any questions at this point? Okay, feel free to leave actually questions in the Q&A section, because it's going to be much easier, because I have a lot of things to say, and I try to say all of them. So,
Even one question, are the transactions being transferred to the follower in a streaming manner?
yeah, it could be if the replication is asynchronous, but it can also be synchronous if it's the synchronous replication style. For example, here some form of RPC. But it depends. Usually, we're actually using streaming for the replication or asynchronous replication when the consistency model is going to be eventual consistency. So eventually, I want all the nodes to agree on the state.
Okay, thank you.
So we on the last whiteboard to talk about the idea of state machines, that we can model actually the state of the database as a state machine, although the states are not predefined and they are not finite. The actual data is the state. And we can actually see that we can replicate the state from the leader to the follower of the replica by actually reading, sending and reading and reapplying the entries from the transaction log. And here is actually the natural coming in idea that we can use replicated state machines in order to replicate data from one node to another. Of course, why we need this? Well, as I said, we need this either to be able to also serve read queries from followers if we are dealing with strong consistency, or also to just have a copy of the data if the leader node crashes and we need another node to fall back and take on the queries, basically to achieve high availability. Okay, so we can now go back to slides. See, there's something in the chat. Let me check. Okay. So we now come to the idea of consensus algorithms. Why we need consensus? Well, because we need to have a way to agree on the state of the database, which, as I said, from theoretical point, we're going to model as a replicated state machine. So there are different consensus algorithms with which we can achieve this. The most common is Paxos, which was designed by Leslie Lamport. Is one of the big names in distributed systems. But the problem with Paxos is that Paxos is actually a consensus protocol over a single value. This value can be an integer, can be a byte array, or something like this, but it cannot be multiple values at the same time. So this is why we have multiple Paxos. The problem with multiple Paxos is that there is no, right now, no agreed actual implementation of multi-Paxos, which is how to achieve consensus over multiple values. And this is one of the problems with Paxos. But the bigger one is that actually Paxos is really, really hard. It's not easy or trivial, but it's good from theoretical point of view when we can prove the correctness of the algorithm. But usually people end up with implementations that are not easy to prove, and a lot of the implementations are actually not proof even today. But we have another version of Paxos algorithm, which is ePaxos, or efficient Paxos. So this Paxos variant is actually leaderless. So you actually don't have a designated node that's leader that's dictating the order of the changes. And we have Raft, which we're going to talk about. We also have ZAP, which is the algorithm used in ZooKeeper, which is an abbreviation of ZooKeeper Atomic Broadcast. And I'm actually having this in my slides for a reason, and this is because actually consensus and atomic broadcast are actually equivalent in terms of distributed systems. You can achieve either one by having one. So if you have a consensus protocol, you can achieve atomic broadcast. If you have atomic broadcast, you can trivially use this to achieve a consensus protocol. Also, atomic broadcast is also known as total order broadcast. So this is actually a way to have all of the nodes in distributed system, have all of the messages in the same order eventually, but we can either have all or none, hence the atomic part. We also have a KRaft, which is a version of Raft, which is actually event-based. It's an asynchronous version, and this is actually used in modern day Kafka, where they have decided to ditch ZooKeeper because of the need to having to manage it. We're going to talk about this. I personally don't know why they haven't came up with this idea much earlier, because for anyone who knows how Kafka works, it seems very natural to actually to have a Raft directly embedded to control the metadata, but we now have it, which is good. And we also have a whole family of algorithms which deals with consensus in blockchains, but the tricky part is that those consensus protocols need to be Byzantine tolerant. So what we mean with Byzantine tolerant, we usually talk about having the protocol be able to tolerate random or any kind of behavior in the systems. So this might be some malicious actors that try to confuse, or this might be normal failures that happen. So some nodes may go down. There might be network partitions. So we might temporarily have no connection between some of the nodes of the system. But those algorithms are much harder both to understand and to design. And they also work with the higher assumption that nodes might behave arbitrarily. So we need to take account of this. The Raft protocol works on a much simpler model, which is with partially synchronous networking model and also crash recovery mode. So we're going to talk about a little bit about those two things. So partial networks is actually the way usually our current networks work. So you have usually some kind of bounded latency. Well, it's not bounded, but you can derive some theoretical bound on the latency that most of the cases will be observable. But from time to time, we might have total partitioning where networks gets disconnected, or much larger delays and hence latency when we communicate. But the assumption is that usually the network is more reliable. Of course, we know that networks are not reliable, but usually they appear to be. And we all know how this is achieved with TCP, I hope. So why Raft? First, Raft is presumably the simplest consensus protocols among all that are currently available. And the reason for this is that actually Raft was designed with this goal. It was designed to be understandable. It was designed by a PhD student in Stanford. You can directly go and read his original dissertation, which is available at this link. You can also watch the original recording of he presenting this dissertation on the second link. And the first one is kind of like a smaller version of the presentation, which is more modern day. And I highly advise anyone interested to go and check all the resources. And we also have one of those two links. I believe the second one was talk as part of Martin Kleppmann's series of distributed systems, and the other one was introduction to Raft made by, I believe it's Strange Loop or some of those kind of conferences. But if you need a much simpler explanation, you can go and check those. And of course, as part of the Raft GitHub page, and also the dissertation, you will find the following text there. There are significant gaps between the description of Paxos and the need for a real-world system. The final system usually have a protocol that's unproven. And this is actually the case in Chubby. And for those of you that don't know what Chubby is a service that provides distributed logs, which it's highly persistent service. It was designed in Google, and it's also kind of like the foundation for etcd, which we'll talk about in next slides. Oh, actually, in this slide, we're actually going to talk about the ideas of Raft. First, are there any questions? Please send us. Yeah, the recording will be available at the YouTube channel of the Tech Meetup series, and I believe the presentation will be sent in the Meetup. But you can always contact me and get either. So what's the idea of Paxos? The idea of Raft, excuse me. The main idea behind the Raft algorithm is the notion of term. So we have terms, and those terms are like periods of time. Here we are not talking about any form of time measurement. We're not talking about physical clocks of physical time, or also not talking about logical clocks. In actually Martin Kleppman's explanation of Raft, you can also understand why we cannot use logical clocks for achieving consensus. But we have the notion of term, and each node can assume one of the three roles. So we have three kind of roles. We have the follower role. We also have the leader role. Actually, no, we have the candidate role and the leader role, and we can transition between all the roles. So initially, all nodes start in the forward row, and this happens either on initialization, so when we bring a new node, or after recovery. So as we said, the Raft algorithm works with partially synchronized networking, and it assumes crash recovery mode. What does this mean is that one of the nodes may crash, but when it comes back, it will try to recover its state. Or if it's a brand new node, for example, we completely lost one of the nodes and we spin up another, we are actually going to be able to recover the state of the system into this node. And this happens with the replication. And it's actually a replication of fork, the same idea for the database. So whenever we start a node, we enter the follower state. And if we have a timeout and we have not received from any leader, we actually enter the state of candidate. So this happens from a timeout. There are two timeouts in this algorithm, and one of them is when we don't hear from the leader. And in this case, we, of course, with any reasonable human modeled voting system, we decided we're going to vote for ourselves. Hence, we became the candidate. One thing that I actually forgot to mention is that in the Raft protocol, we have a designated leader, and all other nodes are kind of following what this leader says. And of course, the leader is the one who accepts the rights and who dictates the order of those rights to the followers. So when we are at the candidate state, if we achieve a quorum from voting by other nodes, we may assume the role of a leader. This quorum happens by voting. And the the quorum mode used in the Raft protocol is majority quorum. So this means that if we can tolerate up to F nodes, then all of the nodes in the system need to be to F plus 1. So if we have n nodes, if we take n plus 1, we divide this by 2, and we take the ceiling of those. We need at least those number of votes for our intention to become a leader in order to really assume the role of a leader. So during our voting phase, if we get a quorum, we become a leader. But when we are candidate for becoming a leader, we also might come out to a timeout where we cannot gather a quorum. And in this case, we are also again going to try to stay in the candidate role and try again. But in this case, we are going to assume that we are in the next term. So as I said, the key idea here is a term, and term is just monotonically increasing integer value, which starts from 0 and just goes. So this is monotonically increasing sequence. So if we have in a fixed time window, we are not able to find that we can become a leader, we again become a candidate and try again. If we, however, find out that the term in which we decided to vote is actually lesser than the term that any other node has an idea of or thinks it is, we are going to again go back to the forward state. So here we find out a bigger term. Or we find out that someone else should have been a leader. Again, actually, if we are even in the leader state, we still might have happen in a situation where we receive a message that is with hard term, in which case we're also again going to transition back to the forward. So as I said, the key idea is term, and we have also another key idea which is using of walk. And this walk stores the messages or the state transitions that needs to be applied in order to come up to the desired state that the system thought it needs to be. And this walk consists of messages, and this walk is ordered, and each of the messages is actually consisting of two parts. One of the two parts is, of course, the data that describes the message, but the another part is the term. So for each message, we know for which term this message came, and this is the key behind an efficient implementation in the Raft algorithm. So we have a walk of messages. We've described the idea of rows. As I said, each node can be in one of three rows, excuse me. I don't know why I just mistake this word. So we have a term, we have a walk, and each node needs to persist durably some state. As you can imagine, because we are working in a crash recovery scenario and we have a walk, and we need to somehow be able to even tell a node that's brand new what's the state, we need to persist actually the walk, but not the whole walk. We don't have to do this. We can actually persist only the committed part or the whole walk that one of the nodes had, and also we gonna need a commit index that tells us what part of this walk it's committed. So in Raft, the commit index tells us what messages are seen by all of the nodes, or rather not all, but at least a quorum. Because if a quorum of nodes has agreement on the messages, we can actually replicate those messages to all others, because the leader will have either at least those messages or some other maybe. So we can at least replicate all of the messages that we believe that have been delivered to at least half plus one nodes, to majority of the nodes. So we have to persist the walk. We need to also persist the commit index. And of course, we need to persist the term that we believe we are. And one other thing that we need to persist is actually our voting decision. So the vote can either be for one of the nodes, or it can be some form of no, where we haven't actually voted for someone, for some of the nodes. So we have a node in our distributed system, and as we said, this needs to be persisted in some durable storage. So this is all the state that one of the nodes needs to store in order to be able to recover and to function in case of crashes or random restarts, for example. We have other state in the algorithm, but I want to derive this state data. One thing that I wanted to say here. Oh yeah, I wanted to say that we can actually have not the complete walk, or we might have some snapshot of the state. Plus, on top of that, the suffix of the walk that was committed or persisted after we took the snapshot. So this usually comes in a form of more efficient implementation, because if we take the snapshot of our database at some point and only store the updates that happen after this, we can more easily recover the whole state of the database. And as you, or at least some of you may know, when we were implementing normal relational database, we were actually working with the notion of page. So most of the data is actually on the disk, on persistent storage, and some of it's in the memory, in the main memory in the form of pages. And we also have some form of, how would say, stashing carrier, for example, as an analogy from Git. So this is the dirty state where we haven't applied this to the storage, but the idea is that the dirty state is persisted by the write-ahead walk. So we have all the changes that happen in the write-ahead walk, and in memory we have them in the dirty or stashing carrier. And we also have pages that usually are clean and taken from storage, or we might mark them as dirty. Of course, I'm doing this as a way to actually help you guys to go and to look more into how databases are implemented, because for me personally, this is a very key thing, at least for any reasonable software engineer. And I actually see that we're going to have like 15 more minutes, so we need to spin up. So maybe we can talk about the key ideas of how the Raft works. So as we said, we have the notion of term and we have a walk. And we have this notion of leader and other roles. But each node has its walk of messages. Some part of this walk is committed. And we know that at least at some point in time, the quorum of nodes agreed on those messages and also on their exact structure, not just the order, but also the messages. And we have some messages that are not committed yet. This doesn't mean that they cannot be persisted. We can persist at any point, but the idea is that we always know what is truly committed, so what we agree on in our distributed system, and some of the data which might not be committed, but we can always at some point decide to also increase the committed index to some other index. And for example, this way we can increase it and for sure persist those messages. Or we can actually even drop some of those messages which we believe are not committed. So again, the persisting here of the walk is independent from the committed, but at least the committed needs to be persisted. And of course, as we saw in the last whiteboard, we can also have snapshots of the data in order to speed up the recovery and also the what we transition and what we are dealing. Okay, so we have this idea of walk. We have the term, as I said, and we also have the voting thing. So when do we have a vote? We have a vote when a candidate decides that there is no leader and that he wants to be the leader. As we said, each node from follower, when he transitions to leader, is going to try to vote for himself and try he to become the leader. But the idea here is that we cannot actually never have two leaders at the same time, at least from when we talk about the committed data. So it's possible to have two nodes that think that they are leaders, but we cannot come across into the situation of the so-called split brain. Some of you may know what this means. So basically, split brain means that two nodes are trying to dictate the state of the system, but this cannot happen in Raft because during one term cycle, and we can have multiple nodes vote for themselves. But if we achieve a quorum, we're gonna have a leader, or we are not gonna achieve a quorum, and we're gonna start a new voting procedure. As we saw before, we have two timeouts. So one of the timeouts is when a node doesn't hear from the leader and decides to go into candidate state. This was one of the timeouts, and the other timeout was when a candidate fails to become a leader and again tries to initiate a voting for himself. So those two timeouts in the Raft protocol, they are actually for each node they are chosen at random. For example, we might have some lower and upper bound into what the values of those timeouts are going to be, but each of the nodes decides those timeouts at random. And the reason for this is to have an efficient implementation where if we have a lot of leader elections, this is how it's called when a node decides to be a candidate and try to vote for himself, that we are not going to end up in a forever sequence of those leader elections. And we actually have another timeout in the algorithm, and this is a timeout that the leader decides when he becomes a leader, and this timeout is used when he broadcasts or when he tries to replicate his walk. This is the third timeout, and this timeout also serves as a heartbeat for other nodes. So this is actually the way one follower knows that there is a leader. He receives a message to replicate the leader walk, which is initiated by the leader. And when he receives this kind of message, he knows that there is a leader. But how he knows that there is a leader? Well, the key, again, idea is for using of the terms. So if he receives a message from a higher term, he knows that there is some leader, and he goes to this node goes to the following state and tries to replicate. I said that the terming part is one of the reasons why we cannot end up in a split brain situation. The other thing that help us achieve this, or rather prevent having split brain situation, is that each node, when he decides to vote either against or either for or against a given leader election, he can only choose to do so in deterministic way. So if he decides to vote for one node becoming a leader, he's going to always send the same message during the same term. And this is also the reason why in what we persist, the last part was the vote. So if a node decides to vote for some node, first thing he's going to persist his voting choice, and then he's going to try and send his voting message. But the key thing is that he decides if he votes for the node, and if he retries to vote, it's perfectly possible for one node to vote for the same node multiple times during one election cycle, during one term. But he's going to always say that he votes for this particular node. He's not going to say that he votes for the election of another leader. And those are the two key things for not having a split brain situation. Okay, so we have this, and as we said, we have the leader election. We have also the idea of replicating this walk that each of the nodes store. And how these walks get replicated? Well, it's get replicated either when the leader receives a new message that he wants to add to his walk. He may add him here if his walk is ending here, or he actually will end it right here if he thinks that this is his walk. And he's going to try to replicate all his walk. But he's not going to do just this. He's not just going to replicate the whole walk because this actually will be stupid because we might send arbitrary large messages. We probably won't be able to do this, or the whole length of the walk might be just so big that we cannot even achieve this in any reasonable time. So how does the walk get replicated? Well, it gets replicated by the idea of splitting this walk. We split this walk by knowing what's the current length of each node walk. So if we have the walk for each node, when one node becomes a leader, he's also going to receive the length of the walk that the current node has. So let's guess this is the walk of the leader, but let's say we have one forward that has the walk up to this index, up to this message, and the leader walks ends here. What he's going to do when he tries to replicate? Well, he's going to try to replicate from the committed from the offset that he knows that the replica has up to his end. But the key part here is that the replica that receives those messages might actually go and drop some of them. How it's going to drop them? Well, it's going to drop them based on the idea that each message that we send and also persist in the walk consists of two parts. One is the data, and other is the term on which this message has been sent for either replication or has been received by the leader. And when he looks at the terms of each message, he might decide to drop some of those messages. But one of the key things from the Raft algorithm is that it is provable that no node is going to drop messages from his work that are already committed. So if one of the replica nodes who has up to the let's say this is his offset, his index, but the committed one is right here, he might decide to drop some or even all of the messages if he finds out that the messages that he received from the leader are with hard term. But the key thing is that one message is decided to be committed or not only if we have quorum. So if we have quorum, we're gonna decide that to move the committed index and of course persist this change in the state of the system. So these are actually the key ideas. I know that my explanation it's not even full and might be a little bit confusing. What I tried here is actually to present the key ideas and to actually hype you guys to go and learn more on yourself, because as you might find out, if, for example, you watch Martin Kleppmann's slides, presentations, his slides where he shows the pseudocode for Raft, it takes nine of his slides. And there's also 2 mistakes on 2 of the slides. So I encourage you to find those out. And if you want, we can always discuss them. But I will now back to presentation. Go back to the presentation. Okay, so we said why Raft. Very quickly, how Raft is implemented in etcd. It's actually implemented as a separate Go package. It's in this GitHub repo. It's the Raft repo in the etcd/io group. And what's etcd? It's a consistent distributed key value store that's used by a lot of platforms, one of those being Kubernetes, which is very well known. There's also 2 talks that talk about the implementation of the Raft in etcd. The key thing here is that the Raft is implemented agnostically from the storage and from the networking part. So if one needs to or wants to use this package, he needs to provide implementations. But the key thing is that the core Raft is actually deterministic and it's implemented with channel single, or rather the loop that one needs to implement. And my last slide is about KRaft, which is the implementation in Raft in Apache Kafka. As I said, this is actually event-based implementation. The actual algorithm can be implemented this way. There are some tricky parts, but the guys from Confluent made it. You can watch and learn more from those links. Of course, I'm happy to discuss with you if you have questions. Unfortunately, we did not have a chance to talk about this, but maybe in a future tech meetup, I can talk specifically about the KRaft and how Kafka is actually implemented, how modern Kafka works. And I want to thank you guys. And of course, you can, if you want, follow or rather connect me in LinkedIn. I have also a Medium blog where I try to blog at least once a week, which in the past weeks, this wasn't the case. Or you can see my GitHub if you want to, but I don't have any cool things there. All of them are from university, but I have big plans for my GitHub. And right now, I'm going to go to questions if you have.
And I'm also sharing the link for our YouTube channel if you want to see the recording later. And if you're interested in receiving notification and news, also you can follow us on LinkedIn, Facebook, whichever is like preferable for you for similar meetups and other events.
Yeah, I highly encourage you, everyone to subscribe to the meetup of our meetups, basically. And there's one meetup that's very closely, I believe, next to in 2 weeks. Is this the case, Gwen?
I believe yes, the brainware of SAS organization, right? If that's the one that you mean. It's going to be in 2 weeks exactly.
Yeah, and I encourage everyone to go visit this meetup. I'm personally going to be there. So we have a question where the work resides. So the work resides both in memory and also in some durable storage. But of course, the committed part needs to be for sure in durable storage. As I said, in the etcd Raft implementation, this is up to the user of the Raft. So you can, for example, decide to take backups into S3 or some other distributed storage that's highly reliable and not just the disk of the node where you're using it. When Raft comes to life, it's actively used, implemented in a tech we may be using. What are its downsides? Well, downsides of Raft. When it comes to consensus protocols, I think that in the model where Raft operates, there are non downsides. It's proved to be correct, and it's easy to understand, implement. So I would rather say that currently there are none, at least in the model where Raft operates, or the assumptions that are needed for Raft. There are a lot to be said when it comes to consensus algorithms in blockchains. One of those algorithms is the one used in VMware's blockchain, which highly encourage everyone to go and look out. There are a lot of trade-offs to be made there, and a lot of drawbacks and pros and cons in those kind of algorithms. But when it comes to Raft, I think that Raft is the best that we have right now. Okay, I see that Bojan has shared one Wikipedia page. I would say that's not used primarily for distributed hashing. It could be used for this, but more it's actually used for deciding on a leader, or used for distributed walking service as a Chibi from Google. And actually what we have with ZooKeeper and etcd is exactly this. We have actually consensus as a service as well. We can actually use those platforms to achieve this. Okay, so Nikolai shared that it's implemented in etcd, and this implementation is probably the one that I would encourage everyone to look if he wants a real implementation of Raft. And okay, so the last thing is we have the YouTube channel link, and we're also at the time limit. Is there any high urgent question anyone would want to ask, or should we wrap here? Okay, in this case, thanks everyone for the attention. I hope that at least the ideas sparkle some interest in you, and you're actually going to check Raft on your own and try to learn it and understand it. It's not hard. I would say this.
Thank you, everyone. Thank you, Ivo.
Thank you, guys.
Thank you.